welcome everyone. I'm glad everyone showed up for Vox's PhD event. So my name is Jared Alper. I'm one of two of Vox's advisors, PhD advisors. And it's been sort of an honor to be his advisor. I've known him for a long time. I think it was in his second year, he took my algebraic geometry class, second year algebraic geometry class. And I was asking like very detailed questions, like really wanted to get to the core level of understanding. And I was always hopeful he would study algebraic geometry or commutative algebra. Encouraged him to do it and was disappointed when he went in a different direction. But I was sort of lucky enough that he sort of came back, well, to an area of like formalization and AI, which is something I sort of learned at the same time as Bob. Since 2022, we've been learning Lean together and then learning AI together. And then together we've been running the Math AI lab. And it's sort of just incredibly impressive what Vox has done. I mean, it's like not just impressive PhD level work, but running a Math AI lab with like 50, 60 students, including PhD mentors and lots of undergrads, is not just something impressive for like a postdoc level, but it's impressive for a full faculty member to take on that level of responsibility. And not just like sort of that he's done it at all levels, from being the director of the Math Lab to mentoring individual students, and then to his own research contributions, which you'll hear about today. And just sort of on the AI and formalization side, I mean, many of his both individual work and projects he's led have been impactful that are in use by Math AI companies, both big labs and small labs. Like last week's, just give one example, last week's formalization Atlas project by Meta, where they formalized 26 graduate level textbooks to, well, you could argue at the level of quality, but but they used like a Lean design markdown file that Voss had like basically built in one afternoon. So
did they use method conventions?
Yeah.
Oh, nice.
Yeah.
Great.
And he's also talked about theorem search to Amazon, and as now part of the big lab myself, I'm aware of what they're doing, and there are building on like a lot of the ideas that Voss came up with the Math AI lab and his thesis. So without further ado,
Okay. Yeah, that would be great. My name is Tina Gu. I'm a professor of applied mathematics. So Bob started working with me about 4 years ago. So it's kind of unconventional for him, right? So he contacted me and directly say, okay, I want to work too. And I say yes. And then the second day we started working, and he'll share about that part, right? Mostly the numerical methods for plasma simulation. And then later in his PhD, he also got interested in this math formalization to also talk in the thesis. So, all right. So I guess with that, I'll leave the stage to you. So
yeah, thank you. Should we close the door so we're not distracted? Well, it's lovely to see you all here. I see a lot of familiar faces. Yeah, really appreciate each of you. Let me tell you about neural methods for plasma simulation and mathematical formalization. Hopefully, I'll defend. We'll see. We'll see how strong the attack is. So I was told that I should tell you a little bit about my PhD journey. So let me do that. It's slightly nonlinear, with the first 2 years being just all pure math stuff. So the math prelims occupied my first year, and it was actually one of my favorite times throughout my PhD. It was super fun to learn all this stuff. And then the second year, I was doing a reading course with Yulia Fevtsova for a year, learning about homological algebra, learning about category theory, algebraic topology. It was also great fun, but by then I realized that maybe it's getting a little bit too abstract for me. Some milestones that I would like to mention are scattered here. So between my first and second year is when I first heard of Lean and started learning it myself, which later became super impactful. And then in the middle of my second year, Jared and I started experimenting more with Lean, which later became the experimental Lean lab, and then later became the Math AI lab. And then, like Jingwei mentioned, at the beginning of my third year, I started working on plasma simulation with her. I was also lucky enough to do 4 internships at Google, which like really broadened my horizons and was just, yeah, really great fun as well. Essentially all the summers except for the first one. Two more or three more milestones to mention is at the end of my fourth year in the spring quarter, I was lucky to be able to teach my own class. That's something that I always wanted to do at least once, and honestly, once is enough. But it was also the first Lean class at UW. Lean has never been taught at UW before. That's okay. That's not true. There was one Lean course at the computer science department. It was very different style. Let's say it was the first math Lean course at UW. And later, Jared has taught several Lean courses, and also Eric Lavins, the chair of the EC department, also taught several amazing Lean courses. But mine was the first. Also, Jingwei and I published our first paper around the same time, which was very exhilarating to me. It was a really interesting experience, and I really kind of understood the joy of research at that point. It took me 4 years together. And two more things to highlight is in the middle of my fifth year, Jared and I kind of rebranded the experimental Lean lab to the Math AI lab, expanding our research direction from just formalization projects to just general AI for math projects. Unfortunately, I will not be able to talk about those projects in this talk, but I do have the slides. So whenever you're allowed to ask me technical questions, ask me, and if you want, we can talk about those. I will very briefly describe them in the next slide. And lastly, conditional in my defense, I will go work at Axiom Math to do more formalization in Lean next week. I'm moving on Monday. So this is the outline of my research contributions throughout the PhD journey, which is kind of scattered in two big topics, plasma simulation and AI for math. So I will very quickly walk you through some of these, and then the talk will only focus on this, and that. These are the papers where I was either the first or last author. So I will talk about these two in detail, but very briefly, this is kind of the core of my work on plasma simulation. Then I will also in detail start this one, but briefly, this is using transformer models to do score estimation. So I will tell you what those words mean in a second. Here, I'm using the same score-based transport modeling framework to do sampling instead of doing plasma simulation. Here, I prove the stability of the Landau equation in public fiber divergence, as well as establishing an error bound on the numerical method. And the error bound I will actually show. So that will be part of the talk. This paper kind of bridges my interest in plasma and formalization, because here I formalized one of the theorems that Jindu and I have in this paper, formalized it in Lean using Claude. And lastly, these two papers are will not be part of the talk. These are part of the Math AI lab. In fact, many of the people here, in fact, could you raise your hand if you were a contributor to one of these? You should raise your hand too. Yeah, so there are several people here who contributed to these. Very briefly, here we parsed something like 11 million theorems from arXiv and built a search engine over it that performs better than LLM search, at least on our validation set, and is faster. And here we trained large language models, fine-tuned large language models to do error correction in Lean, which also outperforms the best open source model at the time that was 4 times the size. Again, on our validation set. Great. Let me jump into plasma simulation, and this is based on these 3 papers with Jingwei and Zhanfu. Okay, I will spend quite a bit of time on this slide. First, we have this machine in our university. It's huge. It's like almost takes up almost this room, and it produces plasma, which is this hot gas that's essentially like lightning. And when it works, it makes a bang sound and a flash of light. I love seeing it in action. We literally have this machine on campus, so if you haven't seen it, you can just go down there and see it. They run experiments almost every day, almost all the time on it. This is Yuri Shumlak's lab. Yeah, really cool stuff. But okay, why do people do this? The main motivation for plasma, working in plasma, is nuclear fusion, which promises a way forward to cheap, abundant, clean energy. Probably our best shot at satisfying our ever-growing needs for energy. By our, I mean humanity's. And there's a joke that nuclear fusion is always 10 years away, and it probably still is 10 years away, and yet it's getting closer. The 10 years are shrinking. So one big component on the way to getting there is simulation. So why do numerical simulation at all? I mean, this is a physical system. Just run the experiment and see what happens, right? Just do the bang and measure everything. Well, no, there's a couple of issues. One, it is expensive and slow to do the physical experiment. But also, two, you cannot measure everything. In fact, you can measure very little when you do this physical experiment. People do their best, but still, it's very much like a reconstruction from bits and pieces, solving several inverse problems, trying to understand what did the experiment actually show from the partial measurements that were taken. So this motivates numerical methods. So meaning doing the same experiment on a computer, because it's much cheaper. You can do many of them at the same time, right? You don't even need to physically have the device, etc. And when talking about these numerical methods, there's kind of two axes that are important. The accuracy, how well does it actually simulate the real world? Because if it doesn't, it's kind of useless. And two, the speed. If it's very slow, it's also kind of useless, right? So we want a method that can do both. So talking about accuracy, simulating collisional plasma is important. So let me tell you a little bit about what this means. So, okay, plasma is like this gas, but it's also this fluid, and it's also charged. It's many things. And one way to think about it is, okay, it's just like water, but it's charged. So you can simulate it using, kind of fluid equations, but also adding some electromagnetism. But that disregards the collisions of the particles. And these collisions become even more important when we're talking about fusion. So why is that? Well, how does fusion work? Two particles need to fuse together. Specifically, like, for example, two positively charged neutrinos need to fuse together and release energy. Well, collisions, so when two particles meet, two things can happen. They can fuse or they can collide, bounce off each other. I mean, this is simplified, of course. And the collisions are much more frequent than the fusions. So if you're in the regime where fusion happens, collisions also happen a lot. And so not modeling them is leaving a lot on the table. But one reason people don't model them is it's complicated, right? So, okay, one way to model collisions is with Monte Carlo methods, similar to how you can simulate Brownian motion by just, discretizing it, right? In fact, there's deep connections between the equations we study here and Brownian motion or diffusion, which I will not talk about, but it's a lot of the same theory and a lot of the same numerics. But those are noisy. For example, any kind of conservations can only hold an expectation or maybe in some limit with not on the nose. So we set out to simulate collisions deterministically. And when I say we, I really mean that when we started working on this, Jingwei was like, oh, there's this thing called plasma. I didn't know anything about plasma. She's like, oh, try this. Anyway, so I mean, I didn't plan any of this, but now I understand why we're doing it. Okay, let me start talking about a little bit of actual math. So I hope that the general audience will still understand some small parts of it. So this is the Vlasov-Landau equation. And what I want you to focus on are these two terms. So this blue box, this is the Vlasov part of the equation. So this is the electromagnetic effects. E is the electric field and B is the magnetic field. And the red box is the collisional part. And so most of this talk will focus on the collisions. I will brush under the rug how we simulate this. In short, it's a method called particle and cell, which is a classical method, and we did not modify it essentially in any way. So I will not spend too much time talking about that. The next two equations are the Maxwell equations, which just determine the dynamics of the electric and magnetic field. Here, this is a long formula, but don't be afraid. What I want you to look at are these two things, the two green boxes. This is the score, gradient logarithm of f. F is the solution, it's the density that describes the plasma. I will mention in a second a little bit more about what that represents. And what I want you to notice is that these are the only quantities that we don't know. Everything else is known, like A is just determined here, and this is just an expectation against F. So this is actually not the standard way to write this collision kernel. But if you rewrite it this way, you notice that if you can approximate the score, you can simulate this. And so this is what we are going to do. But first, I want you to have a little bit of intuition about this method. So in the real world, mass is conserved and mass does not teleport. Right? We're all okay with that. So mathematically, if you have these two properties, then you get something called the continuity equation or the transport equation or the advection equation. There's many words for it. Which is just to say that mass, you can trace matter, as it continuously moves through space. The analogy that I like to think about, which I think is the analogy that Shumik gave when he was teaching his optimal transport course, is like, imagine that you have a big pile of sand, and it's so many grains of particles of sand, so many grains of sand that you can't keep track of all of them. It's almost like fluid. There's essentially infinitely many of them. And there's some wind that makes the particles go somewhere. And you want to understand where all of this sand goes. Well, one way to do it is to take a finite number of particles of sand, like 100, and just track where they go. And that's exactly what happens here. So our particles, not of sand, but particles in a computer simulation, consist of two quantities, the location and the velocity, right? And what happens to the location is very simple. It should move in the direction of the velocity. I mean, that's literally the definition of the velocity, right? Okay, so that part is clear. What should happen to the velocity? Well, that is governed by the Vlasov-Landau equation that we just saw in the previous slide, and the color coding is the same. This is the electromagnetic effect. And I just want you to not really focus on that. Again, this is the part where we don't really innovate. This is it's well known how to do this. But this is the collisional part. So imagine that there's kind of two components to this wind that moves the particles along, right? The electromagnetic wind and the collisional wind. And this is the important part that I want to talk about. So that comes from the Landau collision kernel. So like I told you in the previous slide, if you can estimate the score function, then you can simulate this whole thing. And so it's clear here. You see these two green boxes. This is the score, or rather approximation of the score. So it's supposed to approximate grad log f. So the question is how to do this. And at this point, you might be getting concerned, because what is even f? If we imagine our particle, our pile of sand, if we only have a few particles of sand, you can't differentiate it. There's no density anymore. It's just a finite number of particles. So there's no score even to talk about. It's not even a continuous density. Well, so what we imagine is that there's some underlying density, and we're trying to approximate its score. The question is how to reconstruct it. The two classical, there's a classical way from 2024, and then there's another way that we're proposing. I will describe both. So the blob method uses kernels. So the idea is simple. If you're trying to approximate grad log f, just approximate f first and then take grad log of that. So how do you approximate f from a sample of f? You ask a statistician, the statistician tells you. You take your sample, you replace each point in the sample with a little Gaussian bell curve, you average all of those. That's it. So this is called the kernel density estimation. And the error bounds are well known, at least for the independent, if the sample is independent. This is essentially the idea behind the blob method with a slight twist, which I will not describe, but it's mostly that. And it works quite well. But I will show you a couple of issues with it. Now, another way that I would like to advertise, I guess, is uses a neural network. Actually, the fact that it's a neural network is less relevant than the fact that it phrases this approximation problem as an optimization problem. And this is very natural. If you've done machine learning, this is what we do in machine learning. You want to approximate something, well, you come up with your loss function and you minimize it. So you turn approximation into optimization. And optimization, we know how to do. We have lots of different nice optimization families. In fact, you could also use kernels here. And there is a paper from 2020 by Mautza that does it. But recently we've seen that neural networks is a particularly nice optimization family for many reasons. And so we can use that. But there's a big issue. So the natural loss to use is the least squares loss, right? This is just like your standard, linear regression, except it's not linear, but regression on the target. But if I knew the score, why would I need to approximate anything? I would just use it. The point is you don't know the score. You only have the finite number of particles. So there's a trick that a smart man came up with in 2005. A statistician, he didn't care about any of the plasma stuff, he probably didn't know. But what he wanted to do is from a finite sample, he wanted to approximate the score, learn the score. And so Hivarin was the name. Is the name. What we can do here is expand the square. So you have s squared, you have the cross term, and you have grad log f. Now grad log f, just forget about it. We're optimizing over s, or rather the weights. So this term is independent of s, so forget about it. This is the plus c that is being cut off by the projector rate. The s squared, that's already great because this is s squared times f, so it's in the form of an expectation. Okay, the troublesome term is s times grad log f, and here it's important the exact quantity that we're approximating. So this is where it comes, this is the exact quantity that it's the score and not some other function comes in. Somehow the score is just a very nice statistical function for many reasons, but this is one of them. So you have grad log f times f. Well, grad log f is grad f divided by f. F cancels, you're left with grad f. S times grad f, you can do integration by parts. So you can do grad s times f, or rather divergence of s. And so you're left with this. That is in the form of an expectation against f, which is great because now you can just replace this, approximate the expectation with an average over the sample. And the sample that we have is not independent, but we just forget about it. It's fine. It will work. It seems to work. Great. This is the idea. Does anyone have questions about the method?
What is the WP?
What is WP? This is just 1 over n. I should have written that. Okay. N is the number of particles, sample size. Yeah.
Is there a fusion term?
Is there a fusion term?
If there's collision and fusion, I will also change the.
This is the collision term. And to compute this term, we only need to know the score because we know A, we know psi, essentially we know everything here. And so by approximating the score, we can approximate the collision term, which then allows us to compute this characteristic, the direction in which your particle should move, which then allows you to solve the full equation that describes fusion. Yes.
This may be a very naive question, but when you're describing the collision, you're approximating this density by a finite number of samples. You're talking for a very, very large number of samples by a small number of samples. And you're trying to model collisions. I mean, it just seems like if you're using a much less dense number of samples, the physics of collisions is going to be very, very different than
Yes, if you were approximating collisions using, your standard like Newtonian billiard balls kind of model, where you keep track of each particle and you literally say, okay, this is going this angle, this is going this angle, they should collide and go these, at these angles. But that's not what happens. First, the mean field dynamics are derived. So smart people, I don't know, I've seen the derivation once and I don't remember how it works, derived from the finite. So consider the billiard balls model that I just described. Consider n going to infinity, where n is the number of particles. Derive the mean field limit from that. That's the equation that governs this whole dynamics, or rather it's called the Boltzmann equation, but from the Boltzmann equation, you take another limit as the scattering angle goes to 0 to get the Landau equation. Then you also consider the electromagnetic effect and you get the Vlasov-Landau equation, which now is like the macroscopic. It's kind of like the difference between tracking each individual H2O particle versus Navier-Stokes, right? So this is like the Navier-Stokes except for plasma.
I see.
The macroscopic.
Tracking the distribution.
Yes, that's right. Great.
So actually, I have so in this optimization, so X and P, they're both in the input, right?
They're both in the
What
input.
is so in the neural network, you have some input, some output.
Yes.
Then you solve the regression.
Yes.
What is the output here?
Yeah, the output is three-dimensional. It's just the velocity, or it's in the same dimension. It's in the same space as the velocity space. So it's just R3. The input is R3 cross R3, space and velocity. So it's just a function. The neural network is just a function from R6 to R3. Very simple. Yes.
Is there a reason why you're only thinking about score in velocity variable and not spatial variable?
Oh yeah, because that's what the equation needs. This is just in the velocity variable.
Okay, so it's like a physical constraint that's showing.
It's just exactly what we need. Yeah, we could also, yeah. But this is exactly what we need for the equation. There's nothing special about it outside of that. Great. Yeah, good questions. Let me move on. I wanted to visualize this as a picture. So this is the score. This is a mixture of two Gaussians, and the points are the samples, and the arrows are the score, grad log f. And the intuition that I want you to have is that where there's more particles, that's the direction in which the score goes, right? Just like gradient ascent. Right? Here, this is this collisional term u that we just saw in the previous slide that is constructed using the scores. So this is like where the particles want to move, along this wind in my analogy. Okay, so this is how the numerical method works. I want to tell you a little bit about some things that we can prove about it. And the first thing that I want to start with is conservations. And this is because, we live in the physical world where mass is conserved, momentum is conserved, energy is conserved. We have second law of thermodynamics that entropy increases, or for mathematicians it decreases, because we like our entropy negative. Do we have all the same properties? Well, for the physical system, for the physical system of equations, we do. I'm not deriving them, but we do. Does the numerical scheme have these properties, these macroscopic conservations? Well, yes and no. So the statement that I can make is the particle discretized time continuous scheme for the Landau collision operator. So outside forgetting about the Vlasov part, does preserve all of these things. So that's nice. What is a caveat here is that this is just for the collision operator. So if you also add in the Vlasov part, I actually cannot guarantee all these conservations. Jingui with her student last year figured out a numerical scheme that does preserve total energy for the full equation, but it's more computation expensive, so I didn't use it for this project, but it is possible. But no one knows a scheme that, at least as far as we know, that can preserve both momentum and total energy for the full system. So that is kind of still work in progress. But at least for the Landau part of the equation, we do have the conservations. So this is nice. At least these macroscopic quantities, are not going crazy. But this is not enough. These are just a few macroscopic quantities, essentially like 0th first second moment plus entropy. What about the actual accuracy of the solution in L2 or some other metric? Well, it would be nice if you could say if the neural network is trained well, if the loss is small, then the numerical solution is close to the true solution. And this is the exact statement that we do have. Well, some caveats. There's always caveats. So we need some regularity assumptions for the initial data. I'm not going into that. But if that holds, the accuracy of the numerical solution, which here I call G instead of F is reserved for the true solution, is controlled by the time integrated loss. So this is the KL divergence. And it's upper at time t, and it's upper bounded by some exponential term. This comes from the Gromboll bound times the time integrated loss. This is the exact loss that we were just minimizing in the previous few slides. This one. It's weighted. Doesn't matter. It's similar. So yeah, and 2 years to prove that. So that's crazy. Okay. Theoretically,
It's the root of the number of parts here.
Good question. Yes, this is yes. Okay. This is before the discretization into particles. So yeah. So what you can do is just imagine, forget about this. Just imagine that this is your loss, and somehow you are able, you just have your density F, and you're just able to actually evaluate this. But you're using S instead of the true score. What happens then? So in other words,
Not sure I understand.
yeah. So this is before the discretization. There would be more error terms if we consider that. And I actually don't know what they would look like. I haven't thought about it. So in theory, this works. But what about in practice? Let's take a look. These are 4 microscopic quantities. Some of them we just talked about in these four plots, and each plot compares the blob method and the neural network based method, or SBTM, on 3 different particle numbers. And the intuition here is higher particle number should be more accurate. Why do we use this intuition? We don't know the ground truth. In fact, this was a major challenge in this project. So it's actually quite hard to understand which of the 2 numerical methods gives you the right thing. But taking a look at the electric energy, which is the L2 norm of the electric field E, we can notice that all the red lines, which correspond to SBTM, are hovering in the same neighborhood, whereas the blob method, for a large number of particles, 3 million particles, is hovering in the same neighborhood. But when you take the number of particles to be lower, the curve is off. And so, this is not proof, but it is intuition that tells you, well, it looks like SBTM is pretty accurate at all particle regimes, but the blob method requires quite a large number of particles in order to get to this, in order to output the same statistics. And we see the same thing here when we look at kinetic energy, essentially the same exact picture. For total energy, we know a little bit more because total energy is supposed to be conserved in the true physical system, even though it's not guaranteed to be conserved by the numerical scheme. And so here, the perfect line would be flat, right? So the flatter the better. And the SBTM lines are pretty flat, and all three of them are, even for a low number of particles. But the blob method really does require a larger number of particles to get better at conserving total energy. This is, in my opinion, the most interesting of the four, and we'll actually come back to it at the very end of the talk. But let me talk about it right now briefly. This is the entropy production. So this is the time derivative of entropy, and well, I already told you that the entropy that I used was the math entropy, and here I'm plotting the physical entropy. So it's up to, there's negative sign there, that's why it's positive. But we know that for any score approximation, it's non-negative. But what happens as time goes to infinity? Intuitively, we should reach some kind of steady state, and in the steady state, there's no time derivative for on anything, and so it should go to zero. But at the end of the talk, I will actually show you a theorem that can shed more light on this. So yeah, but essentially the question is, which one do you trust? These are pretty different, and I will tell you that you should trust me. Oh, and at the beginning I mentioned that we care about speed as well, and indeed SBTM is not only more accurate, at least I try to convince you that it is, it's also 60% faster and takes 2 to 4 times less memory on the GPU. Well, now we should all use this method, right? Maybe not. There are some issues. There are several, but the one that I'm most concerned about is the issue of overfitting. Let's first all look at this picture. So, in the ideal world, you train the neural network for longer, and you just get better results indefinitely. But Kevin knows, because he does machine learning, that this doesn't happen. There's the issue of overfitting, and the way that they deal with it in machine learning is you look at the validation loss, and when the validation loss stops going down, you stop. This is called early stopping. The model should not memorize too many details about the exact training data that it's training on. Here, I'm using the training and validation a little bit loosely because the data is really the same. It's the same particles, it's just that the loss function is different. This is kind of like validation in the sense that this is the loss that I actually care about, and this is like training in the sense that this is what I actually have access to during the simulation. So I'm training on this, but I really care about that. Well, what's interesting is there is a very long regime. So x-axis is the number of steps of training. There is a very long regime where the explicit loss, the validation loss, is around 0, but it does start going up. So this is overfitting. And visually, what it looks like is, so this would be underfitting, too little training. This is 10 steps. Okay, this is not important. This is good fitting. Overfitting looks like this, where the neural network, this is the blue arrows, kind of points in a good direction, but it's too long. The lines are too long. I have some intuition about why this might happen, but let's skip that. The point is, you don't want to be in this regime. So I don't like it. This is my main concern with this method. It's somehow doesn't feel like super robust because of this. And so I've spent several years thinking about what to do with this. And when taking the deep learning class last spring, I was learning about transformers, and I had an idea that you could pre-train a network and then use it throughout the simulation without changing it anymore. A priori, it feels like it shouldn't work. because the score function does change over time. I mean, the density changes over time, so the score function changes over time. So how can you have one network predict the score over all time? But the key idea is that the particle locations do change over time. And so if you have a network that can predict the score given a sample, that's exactly what you need. So this is my sample, x1 to xn, from some density. And I train a model that can predict the score of this underlying density, which during inference we don't know, but it's the underlying one from this sample alone. Why is this even a tractable problem? You might say, oh, like how you only have a sample, how could you possibly know the density? It could be super wiggly, whatever. Well, look at this picture. I'm not telling you what the distribution is, but you can just approximately tell that this score approximation is about right. How? Well, look at this point. Clearly, there's more points in this direction, so the score should go in this direction. This is the case for all of them. So you can just from the sample alone, you kind of know where there's more density locally, and so that's where the score should point. This is exactly the task that we solve here. So there's a single model, and I will tell you in a second why the architecture matters, but there's a single model that takes input a whole sequence of particles and outputs a whole sequence of scores. And this is closer, this is like sequence to sequence modeling, just like what happens with, LLMs with, that power ChatGPT, how they take in a sequence of words and output a sequence of words. So the function here is much more complicated than the one we just looked at in the previous slides. Shumik asked the question of, well, what is the input output? It was R6 to R3. Now the input is like, RD times n, and the output is RD times n. So it's much more kind of rich function space. Now, I mentioned transformers already. Why? The key component in the transformer architecture is attention. Essentially, transformer is just attention layers and feed-forward layers. And the feed-forward layers is exactly what we used in our previous experiments in the previous slides. So attention is the key innovation. And the way attention works is, at least in language, each token attends over all other tokens to kind of understand the meaning of this one token. Similarly, and I'm describing self-attention. Here we generalize it to cross-attention too, but I'm just going to describe self-attention. Here it's the same idea where each particle attends over all the other particles to understand what is the density or score at this particle location, right? So like in this particle, it should attend over all the other particles, use them as context to understand which way the score should point. This is very natural. And becoming a little bit more mathematical, what attention is, it's softmax of some matrices, some linear transformations of all pairwise inner products. Now, inner products of what? In LLMs, this is the embeddings of the tokens. Here, it's just the actual particle locations. So this is starting, hopefully starting to remind you of something we just saw, current density estimation, where we also consider essentially all inner products. I mean, not exactly, right? When considering, there's no chalk, okay? When considering x minus y squared, that's fine. When considering x minus y squared, you have, you expand the square, you have x squared y squared, but then you have the cross term, and the cross term is exactly the inner product. So, forgetting about the non-cross terms, the cross term is exactly the thing that attention computes. And so, if you assume that your data is already normalized, so essentially this just reduces the dimensionality, the dimension of your data by 1, not a big deal. Just put it in the sphere. Attention exactly computes the kernel density estimation weights. This is really cool, or rather it can compute. Of course, it depends on the exact matrices that are learned during the training. It can. And in 2 slides, I will tell you that it does. So this is really cool. This was like one of the insights that kind of I had when I was learning about transformers, because I was also thinking about KDE a lot at the time.
But the picture actually changed a little bit, right here, these are size, these are particle velocities.
Yeah.
Right?
Yeah.
But what if you also have locations, positions?
Yeah, you could do something similar. It would not be a big change. You would just train on, data that is 6-dimensional, like location and velocity. It would not be that big of a change. So, does it actually work? I guess I'm following the same template as before. Like I first showed you the theory, and I was like, oh, does it work? Same thing here. I showed you that it can work. Now, does it work? So if you look at the score estimation error, comparing between KD and this model, I called it discoformer, density and score transformer, but also disco. So it's much better, even in dimension 1. You can expect that it's better in higher dimensions because kernels just don't work that well in high dimensions, and Baumgart will argue, but still, I think that's true. But even in low dimensions, at least empirically, we see much smaller error. It also scales well to large number of particles. So here the number that is obscured by this symbol is 17 to the 17, which is only 8 times smaller than the number of particles we used in the previous part of the talk, which was 1 million. So there's no issues here, no weird spikes. The loss is monotone. Yeah, so no issues. And well, I started motivating this paper with plasma simulation. And so let's look at some plasma pictures, or I guess this is pictures of covariance of plasma, not actual plasma. Plasma would be too hot to look at. So here I'm just simulating the Landau equation, not the velocity Landau equation. The Landau equation is quite a bit simpler. And in fact, if you make another simplification, Maxwellian molecules, whatever, I'm not going to tell you what it is, you even know the covariance at every time point. And so we can compare, and we can, you can just see that this conformer model actually approximates the covariance quite well. Here is just the steady state of the covariance. So you don't expect good approximation here, but you expect good approximation then. Yeah, much better than kernel density estimation, or corresponding with the blob method. So, okay, this is some statistics. I also wanted to show you this picture. This is my favorite picture from this entire paper. I told you that attention can compute KD, but does it? Well, it kind of does. And this is a completely emergent property. This is something that is not built in during training. It's something that just happens because I guess it's efficient to happen. So in some sense, KD is a good method, just maybe with many different types of kernels that are data driven. So what am I showing you exactly? The columns are attention heads. Okay, I simplified my explanation before a little bit. A transformer doesn't just have attention and feed-forward layers. Each attention layer actually consists of several attention heads, and each attention head learns its own attention mechanism. So it kind of decides which tokens are important for which other tokens separately. And the rows are different distributions with different samples from those distributions. So this is not the same distribution, right? The whole point of this framework is that you can throw in a new distribution at this model, and it will still approximate the score quite well without additional training. So let's inspect what the attention heads actually learned. Let's look at the 0th one. Here, the red point, which I guess is hard for you to see, is the point of interest that we're looking at attention for against all other points. And the color represents the value of the attention score, magnitude. So clearly, head 0 learned a Gaussian-like narrow kernel. Head 5 learned a slightly wider kernel. Head 3 learned a kernel that is not centered at the point. It's like shifted down consistently, right? I'm only showing you 3 pictures, but I've generated more. My favorite is head 1. It learned a non-local kernel. Normally, we use local kernels, meaning the kernel looks like this. or something similar to that. But here, the attention scores are higher for particles that are further away from the point. That's interesting. And you wouldn't expect all of them to learn this, but you maybe would expect one to learn it, right? Because it is useful to look far away. Yeah, so this is a completely emergent behavior, and I thought it was really cool. Now, in the last 5 minutes of the talk, I want to tell you about the second part of my thesis, which is formalization. Right. So, but first, I want to tell you a story. Let me tell you a story. So, last year, from November to January, I collected about 1,000 different simulations of of Vlasov-Maxwell-Landau system, each one taking about 6 hours. And each one averaged something like 100 plots. So it's like 100,000 plots. Okay, that's a lot of plots. You cannot look at all of them. And it's really hard to all of them compare blob and SBTM. So you have all these plots and you're like, okay, how the hell am I supposed to tell which one is better? When they show the same thing, okay, you can maybe trust it. When they show something different, like this picture is pretty different from this picture, which one do you trust? Which one is correct? And so looking at the data, making various kinds of plots, I was like, well, it feels like the equilibrium should be Maxwellian. There's also some physical intuition for why this should be true, which I think I will mention in a second. But essentially, I had this conjecture that, to be fair, people in the literature, in the community also seem to have the same conjecture that the equilibrium of the Vlasov-Maxwell-Landau system should be Maxwellian. So this was from the data, and then I searched literature. I couldn't find anything. And then I was like, "Hey Gemini, is this true?" And it just told me it's true, and it gave me the proof, and I checked the proof, and it's correct. I was like, "What the hell? This is crazy. Let me make sure it's 100% true." So I decided to formalize it in Lean, and that took 10 days of mostly just Claude iterating on it. Skip it. And it's been verified. Well, let me state the actual theorem. So in the Vlasov-Maxwell-Landau system, the equilibrium is unique, and it's a global Maxwellian, same discussion. And we know its mean, we know its variance, we also know the equilibrium electric field, which is 0, and the equilibrium magnetic field from conservations. So yeah, the reason that I say this is not entirely novel is because in the literature, so when analyzing PDEs, people often linearize them, and what they linearize around kind of gives you an idea of what people expect in the long term, in the long run, and people linearize around the global Maxwellian. But there's never a conjecture stated that like, oh, it should be Maxwellian. So this is, in my opinion, a new finding, and it finally gives us a way to compare these two things. So again, this is the entropy production rate, and well, we know that Gaussian is a global minimizer of entropy given a fixed variance. So what you expect here is that this should go down to 0. In fact, this derivative of entropy, time derivative of entropy should go down to 0. And this is exactly what SBTM has. In fact, this is exponential because this is log scale. And the blow method kind of seems to plateau, even for a large number of particles. And so, what was really interesting to me is that this, full life cycle of mathematical research, where we started with the data, we didn't know how to interpret the data, we made a conjecture based on the data, and AI, then we did literature search, then proved it, and then formalized it or verified the proof. This whole life cycle was like very heavily assisted by LLMs, which is very inspiring and also very scary. But I thought it's like a very interesting prototype of what research in math might look like, very soon or maybe even now. Great. So in conclusion, I'm 1 minute 30 seconds over time. I kind of told you about three themes that I want to emphasize. One is that using a neural network as a subcomponent of a PDE solver seems like a really good idea to me. It gives you something that's fast, accurate, and has provable guarantees, unlike, for example, not using any neural networks, which would be less accurate, or using a neural network to learn the whole solution, which would not have any kind of guarantees. For example, physics-informed neural networks or like neural operator learning, like it's very hard to prove anything about them because it's like very global learning task. The second theme is that score estimation very nicely bridges PDE, statistics, and generative AI. I think it's a very interesting interplay, right? We saw how it's useful for plasma simulation. We saw how it's useful for statistics. And I didn't tell you about it, but obviously in the past 6 years, it's been used to generate images, right? Diffusion models. And the last thing that I talked about is how using combining LLMs and Lean gives a way to this like guaranteed correct mathematical discovery. Modular many things that Jared would love to point out, but yeah, it's still more correct than not checking it and just relying on the LLM output. Great. These are the references. Yeah, that's it. Thanks.